Hello everyone, my name is Ian Bendig. Today we'll be going over the definition of a function. Alright, so the text we'll be basing this off of is A Book of Set Theory by Charles C. Pinter. Okay, so here are two little excerpts from the section on functions. So here's the definition of a function. A function from A to B is a triple of objects f, a, b, where A and B are classes and F is a subclass of A cross B, where this cross is the Cartesian product. And it has the following properties. The first property being that for any x where x is in A, there exists a y such that y is in B, such that x comma y is in F. The second property is if x comma y sub 1 is in F and x comma y sub 2 is in F, then y sub 1 is equal to y sub 2. So this is just by definition of a function. Okay. So we also see here that it is customary to write f colon a right arrow b instead of the triple. I opt to use the triple. So we also see this convention, and this is the main part that I want to discuss. Y equals f at x has the same meaning as x comma y in f. So you can read for yourself how the new form takes hold in terms of the conditions here. Okay, so what do I want to get through? First, you can read this on your own. Okay, so you're done reading that. Here, I want you to remember this set theoretic construction. This set theoretic construction will be used in the proof here. So actually, we can put it in. Note that this is not an assumption. This is a construction, so we are allowed to put it in here. And since this is a schema, it is a schema, so we are allowed to do it this way. But please remember this. Okay, so what are we trying to establish here? We're trying to establish that if I want to establish that the notations are equivalent. So the notations are equivalent here. So x comma y is in F. If and only if, well, we must ensure that x is in the domain of F. This notation by itself does not ensure anything. So we must include this. Okay, so this is our goal. This golden line is our goal. Okay, so this is a if and only if proof. So here's the first sort of thing. We are trying to jump from here to there. So from line A to line E. And then later we're jumping from line A to line E, from 8A to 8E. Okay. All right, so we begin. First, we assume that A comma B is in F. That's all fine and dandy. Then furthermore, in a more nested assumption, we assume Z is in B. This is some element Z, be any element. It is any element. And then we have this and statement here. And then we quantify, use existential introduction of the y as our quantifier over the b. And as you'll see that from the construction here, that we can set, well, I chose f as the thing that we quantify with. That's sort of bad form, but f at a is equal to and anywhere we have an x, we put an a. Okay, so here we obviously have the membership introduction. So we can see clearly that this is allowed. Okay. So how exactly am I saying this? Well, z is an f at a. Okay, so any instance where we have, so putting z in here, if we put z where z is, well, nothing changes, so it just holds. Okay, so we're good here. Next, we assume z is an f at a. Okay, how is this working for us right now? Well, right now, we have to use membership elimination. So see that we can just stick this here because of the membership sign. Next, we use, this assumption is based on existential elimination. So we put the y tildes instead of y. This is and elimination and elimination. Okay, so where is this coming from? This is coming from here. Which one is it? It's coming from F2. This is F2. So here, forgive me, I didn't write the quantifiers in the way that I guess you should do. So that's sort of what we're doing here. Okay, so first of all, we have the statement here. Then we have get rid of the x. What are we replacing x with? We're replacing it with a. Next, we are replacing the y1. y1s. What are we replacing y1 with? We're replacing it with b. Next thing we are replacing is y2. So we're replacing that with y tilde. Y tilde. And since we don't need the outermost parentheses, we'll just be getting rid of that. There we go, looks nice and pretty. Oh wait, we didn't really need to do that because we already had the statement here. So we'll just get rid of the statement there. All right, so now let's find, where is this coming from? Well, we have here, one of the things are coming from here, and another of these, this one is coming from there. So we can have the ands, join it with the and. And where is this coming from? Well, we just use modus ponens on here, with this as the antecedent. There we go. So now, where is this? There's a chain of equality happening. So b equals y tilde. B equals y tilde. So where b equals y tilde, z is in y tilde. So we can replace y tilde with b, and z is in b. There we go. And then, since this whole thing, this assumption was given for existential elimination, we go all the way down here. Since there is no instances of y tilde in this statement here, we're allowed to pop it out. And what is happening here? And then we have our if and only if statement from here to here and from here to there. Okay. Then since z, well, we should have chosen something else instead of z. Should have chosen like c or d, but z is not a variable, it is a name. So we can instantiated for x, where x is a variable. So then we continue here with, after applying for all introduction, that by the axiom of extensionality, that this is indeed holding. This is the same as that by axiom of extensionality. Okay. Then we have here, well, what is it? What is going on? Okay, this implies that. So A over there implies E over here. That's perfectly fine. This is an if-then statement. Then we are allowed to instantiate Y for any B, since B is not in the assumptions, in this scope of assumption, since we are on the outermost scope, or leftmost scope. Okay, so that's all fine and dandy. Okay, so this will be useful in the proof next here. Okay, so now we have, if f at A is equal to B, and A is in the domain of F, well, we assume these two things. Maybe we should have written it this way here, since when we have it written down there, it looks a little bit different. We're just sort of matching it really nicely. Okay, so anyways, and elimination doesn't really matter which way you have it. So this is all still valid. F at A is equal to B. That's coming from the and elimination. This is coming from the and elimination. This is an application of the membership elimination, which, as you might recall, domain of F. This is exactly the same thing as saying this by definition. Then when we use existential elimination, we're using this as our assumption here, where we instantiate y tilde for y. We have a comma y tilde is an F. And we also have this statement here. And where is this statement coming from? Well, we've shown from previous work that this holds. So we can put y tilde for y in this pink statement. Or I think it's pink. That's why we highlighted this as pink, because it's coming from here. Okay, and that we're allowed to do this since this falls under the scope of anything that comes before it on the left-hand side, or the leftmost scopes. And we're using modus ponens because we have already assumed from here. Okay, then f at A is equal to y tilde. That's our consequent. It's all fine and dandy. A comma B is an F. Where is this coming from? Well, we have this here. And we have this equality here. So let's follow the chain of equality. So f at A is equal to y tilde. So y tilde f at A B, so y tilde is equal to B. We can put B in for any y tildes. So there's a y tilde there, we can put a B there. That's where we get this. Okay, so since we used existential elimination for this, remember this is being put into here. This is putting into here, and this is our assumption for existential elimination. There are no instances of y tilde in this statement here, so we're allowed to pop it out using existential elimination. Okay, now we can finish with our if and only if introduction, or material biconditional introduction, whatever you would like to say. Doesn't really matter to me. And where is this coming from? Well, let's see here. When we did this, we assumed this first line in A, and then we got this line in E, and then here we got a line A, and then we get this line E. And are they of the same nature? Let's see. Line E. Well, we might want to include one more thing here. Is that, well, indeed, there exists a y such that a comma y is an f, and then by definition, a is in domain of f. So we might want to also put a in domain f. And don't worry, all this line is still valid, since any sort of thing that has from A, it could be from A to B, then we could say A implies B, A implies this line C, A implies anything G. It still implies what we need to imply over here. So everything is still valid. Okay, but we just needed this to sort of formalize what's going on for sort of this line here. So now we can actually say if and only if that A comma B is an F, if and only if A is in the domain of F and F at A is equal to B. Then we use our just quantify over the statements here, quantify over, and just check that AB is not, A or B is neither in any of the leftmost assumptions, and it's not. So we're good. And this concludes the proof for why these two things have the same meaning, that x comma y is an f is the same thing as saying f at x is equal to y. Now, you might be wondering why I even bothered to do this at all, and that would be a very good question. I have to surely give an answer for that. Well, let's go back to this statement here. Y equals f at x has the same meaning as x comma y in f. Well, from definition of function, we know that y will be unique. So it's possible just to assign a unique notation for y, that is dependent on f and x. That's perfectly fine. But this is sort of a definition by characterization, and sort of introduces more things than you would know. It's kind of sort of a pernicious thing. And what do I mean by that? Well, look at the notation here, that this is an equal sign and this is an in sign. Unless you were familiar with how to create definitions by characterizations, then you wouldn't, at least formally, be able to sort of interchange between these two things. Okay? And furthermore, you still need x to be in the domain, and the information from here provides it, but this doesn't explicitly provide it. We could have put, for the example, if we have f at x, where f is from real to real, like those are our domains and codomains. If we had f at I, then this notation would be meaningless. But if we construct f at x in the manner this way, then we'll actually have something to write. So our notation will always be working in some way. Maybe it will give us the empty set or something. And indeed, that is the case. If we put something like that in there, it will give us the empty set. That f at x will be equal to the empty set if, say, we put a complex number in here with an imaginary part, then y will be an empty set. Will be the empty set, I should say. Okay, and just to reiterate, these two symbols are not the same. So to say that they have the same meaning is sort of a interesting thing to go through if you don't think about it too much. Like intuitively, it's fine, but intuition is never a good thing to rely on, especially so early on. You should be a bit more concrete with your understandings of things. We're not learning religion here, we're learning math. Sometimes it could feel like we're learning religion, and I try my best to stay away from that. So don't take it on faith, take it on construction, right? The only things you need for faith are, well, I guess being able to read. That's the only thing you should take on faith, that I can read. But even then, you can demonstrate empirically that you can read, but sort of an interesting philosophical quandary you can go through. But anyways, my point is that I want to be as concrete as possible when establishing the equivalence between these notations. All right? All right. And there's an airplane. Airplane. So there we go. We're done. Oh, we'll put a little box just for fun. Oh, it's a golden box. It's a special golden box, but you know what? I don't like that. No color. And we're going to get rid of this. There we go. Now it's done. The only thing left, if you really wanted to go through it, is, well, here. Next, well, there's some more little things that you could go through. There. And then each of these steps here can be demonstrated using some sort of rule, either membership, elimination, membership, inclusion. How I use membership, elimination, and inclusion is it's quite broad, and technically we would need to use a little more than the steps that we're using, but I'm already scrupulous enough, so I'll save you the writing. All right. So anyways, if you have any questions, please do leave them in the comments. And I hope to see you in the next video. I don't know what I'll be writing about, but it'll be about something. But thank you for watching, and bye.